Hi, I am Roberto Andolfato. I'm an electrical engineer at SINT Ingegnaria, and I work to the development of and marketing of the program XGSLab. Before starting this webinar, I invite you to see, when possible, the preview webinar by my colleague Michael Antonischen. This webinar gives a quite complete overview of the program XGSLab and describe the main features of the four modules: GSA, GSA FD, XGSA FD, and XGSA TD. Anyway, XGSLab includes other two modules, a soil resistivity analyzer and a Fourier analyzer. These two additional modules are integrated in the program. Today, we will talk about grounding system analysis, and we will go in depth with the module GSA FD. Unlike the preview webinar, we will use only a few slides for an introduction, and then we will use directly the program, and we will show how it is easy to perform a calculation of a grounding system using GSA FD. Before starting with the XGSLab program, a short overview of the module GSA FD and its strength points. GSA is a module for earth grid calculation and design in the frequency domain, including soil resistivity analysis, and represents the state-of-the-art of grounding software. GSA FD can consider uniform or multi-layer soil model with an arbitrary layers number and takes into account the frequency dependence of soil parameters and the propagation effects. GSA FD can be used in the frequency domain range from DC to more than 10 megahertz, and after 10 megahertz the calculation accuracy gradually decreases. Moreover, GSA FD adopts a rigorous electric model of conductors, including self and mutual impedances, and overcome the equipotential condition of the electrodes on which GSA is based. A few competitors take into account self-impedances effects, and a very few competitors consider the mutual impedance effects, and these can lead to significant error in calculation. With the equipotential condition hypothesis, the maximum touch step voltages are widely overestimated, and this may result in grounding system oversizing with additional costs, sink having even 50%. Neglecting the mutual impedances can lead to errors over the 20% in calculation. GSA FD accuracy can allow a significant cost saving in grounding systems, construction, and materials. Finally, GSA FD can consider the most used standard, the international standard EC, the American standard IEEE, and the European standard EN. This slide summarizes the main assumption on which GSA FD and GSA modules are based. As evident, GSA FD model is much more sophisticated than the model GSA. This figure gives an answer to the common question: why GSA and GSA FD, two different modules? This figure is the result of a parametric analysis and represents the application domain of the two modules, GSA and GSA FD. The analyzed parameters were grid size D, the diagonal of the grounding system, the soil resistivity, and the frequency. In a few words, GSA can be applied below the red dot line, and the GSA FD can be applied in all conditions. When the system is big, the soil resistivity is low or the frequency is high, GSA FD is the only possibility. In other cases, GSA is a cheaper and faster alternative. Now my colleague will describe GSA FD step by step. In order to limit the calculation time, we will use a simplified grid model. More complex scenarios are of course possible and will require the same calculation procedure, but more time. We hope that at the end of this webinar, the importance of using advanced model for grounding system analysis will be evident. Thanks.
Hi, I am Daniele Cuccarollo, an electrical engineer at SINT Ingegnaria as well. So I'm going to present you the software running, and so you can evaluate it in a better way. First of all, let's concentrate ourselves on this start page and on the main tools. Obviously, you can see that there are the common tools, the one to create the file, open, and so on. I would like only to make you notice that there is this setting session, this setting window, where you can set many aspects of the software, many aspects that you will see during the presentation. So, for example, the language, some performance parameters, and also the colors are not fixed, but are completely can be completely customized. So this is about the general overview of the software. We can start with the creation of a project. So we can click on New. We can choose the path where we want to save the project. Okay, once the project is created, according also to the license available, you can choose the module that you want to work with. As I said, we are going to work with GSA FD. That is the most powerful tool for the study of earthing systems. We have to do one step. First of all, the choice of the reference standard. So we can click on this icon, and in this panel on the left side of the screen, we can choose the standards, the standard we want to use as reference for touch and step voltage analysis and for some other tools. In this case, we're going to use the IEEE standard 80, and we can go on with the project. The second part deals with the physics of the project, so we have to choose the waveform that with the GSA FD module, the only waveform available is sinusoidal, and in it we have to specify the frequency, and in this case we are going to work with 60 Hz, and we have to apply. Once we have applied, as you have seen, we have this icon enabled. So another typical characteristic of this software is the step-by-step way of working. So the software drives you inside through the right path of the working path. And so it drives the user through the right sequence of working. So now we are compelled to choose the soil model. As you can see, we can choose among uniform, multi-layer, and multi-zone model. Now we are going to choose the multi-layer soil model, a very typical solution. we can input directly the model, or by clicking on this icon, calculate, we can input some resistivity measurements in order to calculate the soil model. Just a moment that I can organize in a better way the monitor. Okay, so now in order to input the model, we need some resistivity measurements. We have these measures in this Excel file. We can copy them. Consider we have these measures arranged into 3 columns: the column A, the column C, that are the electrode distances, and the column rho, that is the measure. So once we have copied, we have to come back to the software. We have that the measure type is not R, but it is rho. And we are not considering the probe depth. So this is the right setting before pasting the values. So now we have pasted all the measurements. And in this picture, we have a quick look of how they behave on the depth of the soil. Consider that this picture is useful to understand which is the most likely soil model to be applied, the most likely layer number to be applied. So when you can see that these measures have a characteristic quite flat, you have a uniform soil model. If the characteristic is always decreasing or always increasing the value of the rho, then you have a 2-layer soil models. If you have a minimum or a maximum, you have a 3-layer soil model. And if you have a minimum and a maximum, then you have a 4 layers. Consider anyway that this software can consider up to 20 layers. So as you can see in this drop-down menu, we could consider that number of layers. In any case, we are keeping the number of the layers at 3 or 4. Now we're going to see which is the best one. So we can anyway make some trials. So with the 2-layer soil model, for example, when we choose 2-layer soil model, these tables are populated. These tables are the tables with the parameters for the algorithm that calculates the soil model. So you can see that in yellow color, as in all the software, in yellow color you have the values that you can edit. Anyway, consider that the default values are good, especially for first-time users. Advanced users, let's say that maybe can have some advantage sometimes, some limited times by modifying them. Anyway, consider that the algorithm that calculates the soil model needs the initial values for resistivity. So, for example, resistivity of layer 1, resistivity of layer 2, and for the thickness of the layer 1. Obviously, the thickness of the layer 2 is infinite. The lower and upper columns are the constraints. Obviously, we need some constraints because the algorithm is a mathematical algorithm, but we have to deal with the physics with this algorithm. So we have to keep the values of the results in a range that has got a physical meaning. So we can launch a calculation. So as you can see, the 2-layer soil model has got a quite high root mean square error. If we apply this model, we can view the model on this picture in logarithmic scale. As you can see, the blue line does not follow very well the black crosses, and this is what we have to check in order to understand if the root mean square error is high or not. So we can get back to the calculator. We can choose the 3 layer number. We can calculate it. again, we can see that the root mean square error has dropped very much. So if we calculate, if we apply, sorry, and we have a look at the logarithmic scale picture, now you can see that the blue line follows very well the black crosses. And at the same time, also this characteristic can be noticed in the linear scale picture. Finally, we can have a trial also with the 4-layer soil model. So consider we have with the 3-layer and a root mean square error that is 2.5. If we try with the 4-layer soil model, obviously the higher is the number of the layers, the longer is the time taken by the calculation. As you can see, the root mean square error drops from 2.5 to 2.2. So the improvement, let's say, is not so important, and so we choose to keep the 3-layer soil model. Anyway, we can have quickly a look to the 4-layer soil model, this in logarithmic scale and this in linear scale. So let's get back. We have decided to keep the 3-layer soil model, calculate and apply. And this is all for the soil model. So now we can go on with the layout data creation and importation. We have basically 3 ways to import the layout data, and consider that the layout data contains 90% of the information about the grounding system. We have 3 ways, as said. We can draw it inside the software. We can import it from an external AutoCAD file in the XF format. And, well, we could also create it adding one by one all the spans in a list like this. Obviously, adding one by one the spans is not very easy. So let's have a quick look to the drawing tools, and then we will see in this project the importation way. So if we draw, if we click on draw, we open this, how to say, whiteboard on which we can draw. We can go to the draw group box in the panel, here in the left panel. And for example, let's suppose we want to create a grid that is 100 by 100 side, so we can set the default horizontal length. A grid that is, let's suppose, 1 meter deep, and this grid has got rods 5 meters long, let's suppose. So we can see how quick is the drawing procedure. So we can draw one span, then we can create an array from it. So in this very quick way, we are going to create a grid with meshes of 10 by 10 meter. So we can go on with the other wires. Okay, so another array also from this. Okay, and finally we can add the rods on the corners, for example. Okay, so now you can see that we have created a grid here, a very simple grid. Obviously, we can view it in many ways. We could also, for example, draw something in 3D, for example, like this, I don't know, and so on. So as you can see, we have quite sophisticated drawing tools. Anyway, as I said, in this case, we are not going to use this kind of importation of the layout, but the importation from AutoCAD. So let's delete all the model, all the spans of the model. Okay, and let's go with the importation tool. When you set this, you have this dialog box, and in this dialog box, you have to set the path of the DXF file you want to use as source of data. In this case, we are going to use the DXF file we have created from this DWG file. Consider that in this DWG file we have these layers. So I make you notice we have civil works, I01, I02, and ROD1 as layers. So we can get back to the software. We can choose the path where the file is, in this case exactly in the same folder of the project. We can also set a target for the number, so 1600. We can set this. We have to set the scale of the CAD file. So in this case, we have that 1000 CAD units are 1 meter, and then by clicking on this plus, we can recollect all the layers we are interested in. So civil works, for example, is for background. Background means things that have got no electrical meaning. They just have graphical meaning in order to be able to see, for example, a fence or a road or something like this. So let's go on with the I01 layer. We have to set the electrode which this layer belongs to. It is an horizontal element. Basically, the elements that belong to this layer are horizontal. They are at 1 meter of depth. They are wires with an external diameter of 10.7 millimeters. The cross section is 70 square millimeters, and the material is copper. We have no covering material, and so no thickness for the covering and no covering material, and apply. We have to do this for all the layer we are interested in, so also for rod 1. I'm going to go quite quickly on for this in order not to lose time on this part. The important thing is that you understand that the important thing is to arrange your AutoCAD file in a good way in order to recognize the layers and to collect them in the model. Okay, okay, so now we have completed the parameters we wanted to use in order to import, and we can start the importation by clicking on this button on the left panel of the screen. Consider, before having a look to the model, consider that if you modify the model you have imported and you want to export it, you can also export in the XF file, and so you can have a complete interaction with between the software and the AutoCAD. So we can have a look at what we have imported. So this is exactly what we have seen in the AutoCAD file, and we can also add the background elements like this. So as you can see, this is the AutoCAD, this is the software. So as I said, we have set the target number of elements. We can have a look at the division into elements in order to see if the division is good. So it is quite good, the division into elements. So so now we can see how the elements were divided, so we can concentrate our attention on what is not background. So like this, we can see these elements, and so these elements highlight the elements of the span. So the elements are a very important thing to be considered in order to say that they are the real brick of the calculation. So now we could, maybe we think we are prepared to launch a calculation. This is not true. Anyway, we can try to debug, because before starting, as you can see, the compute icon is not enabled, because we have to run a debug and we have to run a successful debug before being able to launch a calculation. In this case, we still have some data to input in order to be able to start the calculation. That is to say, in this case, we need a fault current. Let's say that the fault current can be known. Many times the client tells the designer which is the fault current to be used to size the grounding system. And some other times we have to calculate it, so we have available this tool, earthing currents, that work according, in this case, the IEEE, in other cases, according to the EN, in order to use the simplified method given by the standard, and in order to calculate the earthing current. Consider that in our plans we want to develop a much more sophisticated tool in order to calculate the earthing current. By the end of this year, we will have this kind of tool. Anyway, in this case, we are going to input the current in this part of the grounding system. So we are going to input it in polar notation. So the modulus is 25 k-amps and the phase 10 degrees. So we can input it. And if we debug now, as you can see, here in the message window, we have that the software tells us that the debug is successful. Moreover, if we have a look to the clean picture, we can see that the software also shows us where the current is injected. Obviously, this is very important information, since this is a software that considers the internal impedances. Now we can launch the calculation. So as you can see, the calculation is not immediate, and it is not so long anyway. Consider, generally speaking, that the calculation time depends on the elements number and on the number of the layers of the soil model, and on the kind of the soil layers, because if you have quite similar layers, then you have not so many problems in calculation speed. If you have very different soil layers, maybe you have that the time is a bit longer. Anyway, as you can see, in this case, in 40 seconds, we have calculated, we have finished the main calculation. So consider also that the calculation part, for the ones at least that are already familiar with other tools that have got similar characteristics, the calculation procedure is divided in this software into two parts. This first part that we have just seen, in which the software calculates all the values of the elements, and the post-processing part. Post-processing part is the one that we will see later, the one of the line calculation and the area calculation, that using the results of the main calculation, the first part of the calculation, generates other results So, for example, for the area calculation, the surface potential, the Earth surface potential, the touch and step voltages, and so on, and the same thing for the line calculation. So, getting a step back, the first results that we have available now, let's start from the GPR and earthing impedance. We have this table. This table is telling us that in the injection point, that we can also call injection, we can name this point in order to make it easier to recognize it. This table is telling us that the injection point is placed on these coordinates, has got this injected current, this external electromotive force, and so it is 0. And very important, this element, this point has got this potential with this phase, and also very important, the earthing impedance that we can see from that point. So by injecting a current on this point, we obtain this earthing impedance. We can also add some other, important points. So if we get back to the layout picture, for example, let's suppose we wanted to add some reference points, as we call them. So we can select some elements, we can edit and add, for example, a reference point. So apply. So we can also see the names of these points. So as you can see, this we have changed its name into injection. We can change this other into, okay, so this is the floating electrode. This is north, this is east, and let me see again, okay, west, and south. Obviously, I am giving some random names in order just to make you see that we have some default names. Obviously, the best solution is using some significant names. So once we have added this, you can see that in this table we have all those points. And you can also notice that even if the injection point north, south, east, west are in the same grounding system, they have very different potentials. So inside the same earthing system, we have around 1000 volts in drop of potential. And this is the very important characteristic of this software, of this module of this software, moreover, because GSA FD is able to calculate the internal drop of potentials. Moreover, we have also that the floating electrode is influenced by default in the main electrode, and it assumes this potential. These things that have been seen on these points can be seen also in this picture, in this distribution potential, that is this. So for each color, you have a potential, and each color is explained in this color code. So as you can see, we have higher potentials here, so around 3,400, and the lower potentials here, where the difference is also 1,800. You have also many other distributions, so leakage currents, for example, so also longitudinal currents, electromotive force, and so on. Electromotive force, and then we can also see it. So we have many distributions that give us many information. Consider also that you can export these results in CSV format, so if you want to represent them in some other tool, you can. And you can also scale these results, so you can avoid to make many calculations with different injected current, but you can scale these results in order to analyze the behavior of the same earthing system with different scenarios of amount of current injected, for example. So now we can go on with the post-processing procedures. First of all, before going on with the post-processing procedure, we should make a very small step backward in order to complete the data input. Let's say that the data input has got two paths distinct one to the other. One path is the physical one, the calculation that deals only with the physics. The other path is the limits. So are the limits. And the limits deal only with the reference standards. This is the reason why we have managed to run a calculation without input, without going to the input of the limits. Anyway, we are going to do it now. So you can also notice that we can change the limits in any moment of the calculation without losing the calculation. So the limits that we can import, that we can set, can be calculated according to the three standards available. Obviously, here we have the IEEE, but it is the most appreciated standard in the world because of its easy to be understood and also to be applied. You could also enter the limits you want, if you want, without calculating them. So if you have some specific standard in the world, you could also enter some other limits. In any case, in this case, we are going to calculate the limits by using this tool, in which we can set, for example, the clearance time in this box. The body resistance is given by the American standard, and so we can only see it and we cannot modify it. We have also the reference of the body weight, and for the moment we keep at 0 the resistance of the shoe and of the glove. The limits calculated are these ones, and then we can apply them. And now we can get back to our post-processing analysis. So let's go to analysis again and area calculation. When we choose the area calculation, we have, as you can see, an area selected and circled by this dotted line. We can modify it by drawing it in this way, as you can see. We can draw it, we can rotate it, as you can see also in this. We can set the parameters of this area in these boxes. We can also put it below the soil surface, for example, like in this way. As you can see, the area now is below the soil surface. Anyway, in this case, we are interested in the calculation on the soil surface, and so we are going to keep the Z at 0, and we are keeping the step length and width. So we have to set the step length and step width. This step, let's say it is the division of this surface, because the calculation we are going to run is a calculation on a grid inside this area, and the grid is determined by setting these steps. In this case, we could also choose this kind of step in order to have an accurate calculation, and we can launch the calculation. Consider that the shorter is this step, the longer will be the calculation time. So the calculation has finished. Now we can have a look to the results of the area calculation. First of all, we can have a look to the Earth surface potential, surface, because this time we have kept a z of the area calculation at 0. So, for example, first of all, we can have a look to the 2D plot of the Earth surface potential. So, in this case, it is very clear that we have high values, as you can read on the mouse that is hovering over the image. The high values are in the substation, here where the current is injected, and then there is a sort of bottleneck along these two wires that connect, let's say in a poor way, the substation to the remaining part of the earthing system. And so the remaining part of the earthing system has got another level, let's say, almost equipotential, not exactly equipotential, but let's say another level. Consider that by unchecking this option, show snap grid in the data display, if we generate again this picture, we can avoid to represent the grid that is background the image. So let's say the results can appear more clean. Moreover, we can have also a look to the 3D version of this image. In this can be noticed very well the difference in the Earth surface potential between the substation area and the remaining part of the plant area. So we can notice that this bottleneck influences very much the behavior of the earthing system. Consider that these 3D pictures can be rotated in this way, so if you do not like the angle in which you have the results, you can rotate them. You can export these results in CSV format, so if you want to calculate inside the software and represent outside the software in some other tool, you can do it. And you can also save the area calculation. Finally, at least for the area calculation, we have the most important part, maybe, that is to say, the touch and step voltages analysis. So, in the American standard, we have only this option available, and we can generate the touch and step voltages analysis pictures by choosing 3 different options. We can choose as a reference one of the points we have set, so the injection point or one of the other reference points. We can have a picture with all points, and we can have a picture with all elements as a reference. We can have a very quick look, for example, by choosing one reference point as a reference and generate safe areas. So in this case, we are generating a picture that that shows which are the areas in which we are in a safe condition if we touch an external conductive device that is connected to the earthing system in the reference point north. This is the meaning of the reference point. Because when you do not have a single potential for the whole earthing system, you need a reference. And so we needed to choose one reference. So, as we can see, the safe areas are not sufficient for sure. We can consider the presence of an Earth surface, of a soil covering layer. In this case, we can consider the presence of a soil covering layer, for example, of gravel. A typical value for the resistivity of gravel is 2500, and the thickness, a very typical thickness, is 100 millimeters. Once we have set the material of the soil covering layer, we have to go to limits, and we have to calculate again the limits that we calculated previously. As you can see, in this case, these two values that previously were the same of these other ones, these values with plus SCL, plus soil covering layer, are different because they consider the presence of the soil covering layer. So we can apply, the values are correctly applied, and then if we get back here, and if we choose this option, SCL, we can generate exactly the same picture of the previous image generation, but in this case, we are considering a soil covering layer made up of gravel and of 100 millimeters thick. In this case, we are always considering the north, the reference point north, as a reference. So the green areas are the areas in which we can stay, and at the same time, we can touch in those areas with our feet in those areas. We can touch an external conductive part connected to the north reference point. This is valid for any reference point. And so if we want to have a picture that considers all the points at the same time, we can check all points option, view 2D, and then there is an image that divides the area calculation into regions. Each region is the place where the closest reference point is taken as a reference. So, as you can see on my mouse, you can see that the pivot is west, but if I cross this white line, the pivot becomes injection. So if I cross the white line, the pivot becomes north, south, east, and floating. Finally, let's say the most refined option is all elements. So if we choose all elements, in this case, let's say that it is an extreme development of the all points option, because each element of the calculation is taken as a reference in order to calculate the touch voltages. So this means that if I have to analyze the safety condition of one place, the reference that I will take for that place is the closest element of the earthing system. And the result is this. Let's say that the difference, this option, this all elements option, and this all points option have different applications, because all points option can be very useful for industrial plants, for example, where the earthing points are many but not very widespread. Let's say that the reference point in an industrial plant can be considered like an earthing bar, something like that. The option all elements is more, is more useful for cases like substations, for example, in which all the devices of the substation are earthed exactly where they are. So let's say that very likely they are earthed to the closest element of the earthing system. These are the image for the safety condition, but we have many other images, for example, well, without choosing the all elements option, and keeping the north as a reference, we can generate again the safe areas, and then we can see that we can generate not only this image that is telling us the safety condition, but also this image, for example, that is giving us the value of the touch voltages, the absolute value of the touch voltages. So this is not an analysis of a safety condition, but it is only the touch voltage that we have in all the area we have chosen, by taking as a reference a reference point called north. At the same time, we can generate a picture that shows us the touch voltages with the color code of the safety areas in 3D, like this. Another very interesting image is the step voltages. Obviously, the step voltages do not depend on the reference point, they just depend on the Earth's surface potential. And so this image does not depend on the option we choose here. And as you can see on my mouse, there is no information about a pivot because we do not have a pivot. So this is all about the area calculation. Consider that for all the colors you have the color scale in the legend, you have information in the legend about the maximum. The minimum value represented the Z of the area calculation, and if the soil covering layer is present or not in the picture we have generated in this moment. We can have another kind of post-processing procedure about touch and step voltages, that is the line calculation. So we have just to click on line, and then we have to draw. Let's say that the line calculation works exactly in the same way of the area calculation. The only difference is that instead of a grid of points, we have a linear sequence of points. So the line calculation, let's say, is, gives not an overall vision of the calculation results, but gives a more specific and local view on the results. So it is usually the area calculation results are used to give an idea of the general results. Area calculation are used to highlight some critical points, and so to ensure, for example, about the safety of some external part of the earthing system, for example. Anyway, in this case, the options to generate the picture are exactly the same that we have seen for the area calculation. So we can choose a pivot, for example, also in this case we could choose north, we can choose view, and so we can see in green color the Earth's surface potential. This violet line is the touch voltage reference, that is to say the potential of the reference point north. The red line is the touch voltage, and the blue line is the step voltage. If we change the reference, for example, by choosing, I don't know, for example, west, and we view again, we can see that the green line is always the same, but the violet one is different. At the same time, we have also the limits represented here in these pictures. So as you can see, the limit stated by the standard in this case is the dot dashed red line for the touch voltage, and the dot dashed line in blue color for the step voltage. And so the red continuous line, that is the touch voltage, is always above the limits. If we generate the same picture by considering the soil covering layer, we can see that the limit is lifted, and in some places the touch voltage goes below the limits. Also in this picture are available the options all points, for example, like this. So you can see that this violet line changes because the closest reference point changes, basically. And so also the touch voltage is influenced by this. And also the all element option is available, and so the changing of the reference is more is more evident and it is more continuous, and also the touch voltage is influenced by this. So as you can see, also the line calculation results can be exported in CSV format. So also in this case, you could generate the picture in some other tool if you want. And also in this case, the legend shows the meaning of everything that you are viewing in the image. Also, for example, the pivot point chosen and also the presence of the soil covering layer. There is one final part of the post-processing procedure. We would like to show you an option available in GSA FD. We can also calculate the magnetic field. We can do it, moreover, for surfaces above or for lines above the soil surface. So let's suppose we want to calculate the magnetic field 1 meter above the soil surface for an area that takes into account everything. Let's do this calculation. This calculation is not so long as the calculation for the Earth's surface potential, so it is something a bit more quick. Let's say that this calculation honestly does not have many practical applications, but it is very interesting to see it because it shows the paths that the current, the longitudinal current chooses in order to go from the fall point to the places where it is leakaged, where it is injected into the ground by the earthing system. So, as you can see, this picture shows the injection point, the current that splits in many paths, then the bottleneck, that is the place where the most of the current is concentrated, and so on. So this is all about the post-processing procedures. We would like to, before the conclusions, we would like to show you an interesting and important aspect of grounding system analysis. And we would like to show it to you by taking as a reference these slides that we have prepared. As known, many software are based on the equipotential assumption, and so they neglect, let's say, the drop of voltages along the conductors, unlike the GSA FD does. So this picture that is taken from the calculation we have just run takes into account the drop of potential, and most of softwares you find in the market do not do this. We know this is possible in some cases, in particular if the grid size, frequency and soil conductivity are lower than a given limit. So many times this simplification is acceptable, but it is not easy to know exactly when the equipotential assumption is valid. In these regards, the results of a parametric study we did taking into account a square and well-matched grid of copper conductors has been described in the introduction, as you have previously seen. Anyway, according to our experience, we can say that the equipotential assumption that in this slide is represented by this second image and that can be calculated by using GSA and not GSA FD. This equipotential assumption can be useful in about 50% of practical cases. In the other cases, it is surprisingly to see that the error related to this assumption is quite important. In many cases, so it is fundamental to take into account the effects of the drop of voltages along conductors, because to consider this, by considering this, we can find out, for example, as you can see also in this slide and this other slide, we can find out that the earthing system is not safe as the equipotential condition that this slide shows. In this case that we have just analyzed in this webinar, we have that the same calculation with the equipotential condition gives a safe a result that is telling us that the earthing system is safe. But if we change the tool into a more sophisticated one, that is to say the one we have used in this webinar, then we find out that the earthing system is not safe, as you can see in this picture. And so you can see some yellow hole that means that the touch voltage is above the limits. So this is due to the effect of the drop of voltages along conductors, and drop of voltages can be related to self and mutual impedances. Some tools available in the market neglect the mutual impedances, but this can lead to serious computational errors, also more than 20%. XGSLab takes into account self and mutual impedances and also the propagation effects. This is the only way to ensure an excellent calculation accuracy in case of large grounding system, soils with a low resistivity or high frequency applications. This is all about the calculation we have presented in the webinar. We can go to some conclusions. Let's say that to conclude this webinar, we can summarize some important aspects. This webinar is related to the module GSA FD of the software XGSLab, the more accurate tool in the market for grounding calculations, because it is the only software specialized in grounding design, able to consider a multi-layer soil model, frequency dependence of soil parameters, both self and mutual impedances, impedance effect, and the most used international standards, IEEE, IEEE, and EN. We have analyzed step by step how to perform a grid analysis, a grid design. We saw GSA FD requires data about the soil model, the grid layout, the current to earth, and the standard limits. As understandable, soil modeling is a crucial aspect in grounding design. The US and Canadian markets in this regards are very demanding, and for this reason XGSLab has been equipped with a powerful soil resistivity analyzer based on the trust region method, a calculation method robust also in case of ill-conditioned problems. The grid layout can be created by using the internal CAD or by importing from a DXF file created by other CAD tools. The debug algorithm implemented in GSA FD helps the user to rectify the data and debug, for example, overlap the lines, doubtful connection, so on. The current to earth and the standard limit can be set arbitrarily or calculated according to IEC, IEEE, or EN standards. In particular, we used the IEEE Standard 80 2013 edition. Despite the powerful and completeness, GSA FD is easy to use also for beginners. Of course, GSA FD, as other advanced modules, requires specific knowledge, but not necessarily an expert user. Expert users and researchers can always appreciate calculation capabilities and rigorous algorithms. So this is all. Thank you for your attention and see you next webinar. Bye bye.